It should be reporting now. Is that?
Yes.
Okay, awesome. I'm just going to do a quick little intro for everyone else. Basically, hello, everyone. We're doing the first workshop of our 2020 workshop series. And I just forgot to record, but I'm just going to run through what I just talked about really quick. So first off, you have some questions why we're here, and I list out all the questions of why, what you might be asking. And I talk about the reason for us doing this. And, you know, the short answer is we want to teach other students everything. We want to teach students all the basics they can learn about robotics so that they can go forward and learn more things. So now off to the new point is who will be teaching these. So I did a little introduction, but same thing. I'm the workshop coordinator. My name is Joe Vaccarella. I'm going to be teaching workshop number 1 and workshop number 3. Workshop number 1 is Intro to CAD, this one, and number 3 is 3D printing. Both of those things I'm really passionate about. So if you have any more questions, you can always message me or email me, and I would love to talk about those things. Fran will be teaching How to CAD, which is our second workshop. She's also an ME, really great at CAD. And then Bennett, our president, Fran's our vice president. Bennett, our president, will be teaching Intro to Programming using Python, forward kinematics, planning with A-Star, sorry. And then I just did to mention the bottom that Sam Treese guy, he was actually an alumni that helped us make all of these. So big thank you to him. He put so much work into this project, and I very appreciate it. But it just goes to show there's a lot of passionate people that even he graduated, but he still wanted to help out the team. So I thought that was really nice of him. Okay, so you might be asking, one of the bigger things is what are we doing? Basically what that boils down to, sorry, I don't know. Basically what that boils down to is we want to make a robotic arm, a 3D printed robotic arm. You might have seen some of the pictures I posted around and emailed about. I hope you think they look cool. I really like how they look. I think they look pretty cool. And so what this is basically made up of, and it's not functionally, it's not that crazy. It's 2 servos and 2 3D printed shafts, kind of rod things. And then there's a mount. And so Fran designed it. I helped with some of the finishing touches. And then Bennett and Sam programmed this thing. And so you can see this is Bennett a picture of what Bennett's making. But we went from a design to a physical thing. And so what this will be able to do, and I'll speak more about this, is it is a robotic arm that can move intelligently through 2D space. So what that means is that you can designate a point on a 2D graph. Say I want it to go here, and it will intelligently know how the most efficient way to get there and what servos to move and bend, and it'll get to that exact point. And so while that may seem simple at first, it actually incorporates a lot of topics that you'll want to know about robotics. Especially, we have the one side, which is, CAD, 3D printing, which is, that's how we design our thing, and that's how we make it physically. That's how we make the whole body of it. But then you look on the right and you see the computer science stuff. Pretty cool stuff that, coming from McNeese side, I didn't know what, I didn't know what A-Star planning or forward kinematics was before this project. But after the fact, I've learned what they are, and I'm like, oh, wow, this is super cool. So, and what I talk about on the top right is if you don't know any of these things, perfectly fine, we will teach you. I had no clue what 2 of those things were beforehand, and now I know, and I think I have a better understanding of how things work now. So what I'm actually going to do right now, because just to get you a little more range of what we'll be doing in the later half of this, I'm going to share my, sorry, one sec. I'm going to share my desktop real quick. This should work. Screen 2. Okay. Okay, so now I should share my desktop. So one sec, sorry. And you should be able to see all this stuff. But what I'll show now is that this is, I'll just show this real quick. This is the code side of things. And what we'll go through is you'll learn all these topics. And one of the things you'll learn, and these are cool little demos of what we'll be doing. There's something, I'll give really short descriptions, and Bennett, you can follow up if you have anything more to say about this. But for one, so A-Star, you might not have any clue what that is, but basically A-Star, what that does is it's a algorithm you can use to plan out the most efficient route to a point given like different like pathways to get to a certain point. What that means is we made this really cool, or Ben and Sam made this really cool little demo. It takes just a second. I believe I have it running here. Let me just run it again. Okay, so can you guys see this thing right here? Okay, awesome. Okay, so you'll see right here, you're like, what is this? It's basically a maze, but what you can do is the cool thing about this is you can see where, like this is where you want to start, and then you can have different goal points. So I'll make a point, put one right here, and then I'll put one like here. And so what you'll see is A star, what it does is it's intelligent, like route planning in a way. That's how I think it is. The ME major, you know, it sounds like it's cool because you can use this for so many applications for robotics. And what we'll do is you see this in this like this cool little demo. What we'll do, which would be nice, was we will help you learn how to like implement the code for this. Not the entire thing, a small tidbit, but it will be very useful to be able to know this, because then with the robotic arm, you can get it to its path the most efficient way. The other demo we have is, the other demo we have is this, which is a visualization of a robotic arm and how it moves using servo joints, so how this moves like that. And so you see, as I move this little peg right here, you can see the arm moving based on that. And this is just in, I believe this is in radians, and this is how much you want it to turn and such. And so both of these topics, we will teach you the basics. We'll teach you the reasoning behind both of these, how to make it yourself, and then resources to learn more, along with implementing certain parts of this code to actually get these two little demos to work. But what this all culminate into is in the end, we'll be able to move that arm in the intelligent manner I was speaking about. Bennett, do you have anything more to say regarding this?
No, I think those are the two main topics we cover. First, he showed A star, and we showed forward kinematics here. I think, at least as a computer science major, both of these demos are maybe less than impressive, but I think we've designed this workshop series in a way that doesn't only like self-contain all these topics, but I think it does prepare you, especially if you're computer science, for further work in these topics. The same algorithms that we're using in 2D end up applying it in 3D in general. And the other note I would add is the A-star implementation that you saw on that grid, the exact same backend is going to apply to the arm as well. And so we end up showing some idea of generality, where we set up some sort of model of what types of objects A-star works over. It's very abstract. And from there, we can reason both over the arm and over the grid using the same code as the center point. It ends up being useful if you're going to computer science to understand these types of things. But of course, we'll get into that during workshops 4 to 6.
Yeah, that's a great point, Bennett. I should have mentioned that. But yeah, the generality of all the stuff that we want to teach is that it's not just supposed to be, oh, I can make a robotic arm. It's, oh, I can do all these different things. I can make an RC car. I can make a drone. I can do all this stuff. And we want to teach you in such a general way that, you have examples to work off of, but you can also, branch off of that and learn more. And I think that would be great for everyone's learning. Is it back? Can you guys see it back in PowerPoint mode? Is it?
Mm-hmm.
Okay, awesome. Thank you. All right, so yeah, now back to your regularly scheduled content. And just for FYI, the workshop's gonna last probably around an hour. Depends on if people ask questions. It took me around 42 minutes beforehand to go through it, but should be around that. Maybe, we'll see. Okay, so today what we're talking about and what we started with is everything you want to learn about CAD. So basically, I'm gonna, tell, as someone who's been using CAD for, I don't know, maybe last 5 years, maybe. I think I'll go into more software side later, but I primarily have used Inventor and Fusion. And so I think I've learned a lot of stuff, and I've taken multiple classes dealing with CAD, and I think there's a lot to be learned, especially, if you've never done any of this stuff before or never heard of CAD, I will go through it. Okay, so you might be asking, some of you, that what is CAD? Well, CAD is computer-aided design, and as stated here, it's used for any modern engineer, most of them mechanical engineer, like industrial, you'll be using CAD to design, whatever you can find in the real world. Most everything you find around you is designed in some way. And so it's incredibly useful to have these skills and know how things are designed so that you can understand better how like engineering works and like how things come together in the projects. Okay, so before CAD, CAD only existed when we had computers based on the computer-aided design aspect of things. Before that, we had drafting. And drafting is basically what you do is because you only have a 2D piece of paper, you draw out different faces of the part or whatever object you have to represent it in 3D. What that means basically is that if you're looking at things from certain directions and then you are drawing a picture of them in only that direction. So if you were to like per se look at this cup, I don't know if you'll be able to see this, but the cup would have a front face, it would have a top face, it would have a rotated like right face. And what you could do is for most objects every object you can represent it in drawings from different angles to like understand how it takes up 3D space. Because before we couldn't represent things in 3D space without making them. CAD is awesome because we can do that very easily. Some people still use drafting. I've done it in classes, but it's CAD's it's more taken over more. So drafting is what you'd call a drawing. The drawing is very central to like mechanical engineering or anything like that in general. Basically, if you want to make a part or anything like that, you'll need dimensions and you'll need to put in values of sizes of measurements of things. So like if you have some object, you can know that it's some height, some width, some length, and what you'll do is you can draw that out onto that page, and then if you want to manufacture it per se, it's very easy to because you have those dimensions. Because for any type of manufacturing that you'll ever do, you need precise dimensions, and just being able to see those on a piece of paper is very useful. And the next point that this talks about, yes, is machining. Machining is just a general term that just regards basically any types of manufacturing you can think of. One of that can include CNC, which is computer numerical control, which is basically if you've ever seen the machines that has a spinning top and it will move around on an axis and it will like cut out things or it will do whatever. You have like a lathe, which is you have something spinning and you're cutting at it. And there's many others. But basically, if you ever want to machine something like that, you will need to give the machinist a drawing first because they need dimensions and they need all that stuff. The cool thing about CAD is that you start off with a part, you make some sort of part, you can export it as a drawing. What you'll do is you'll put it, you can have a 3D object and then in CAD you can export it that way so that you can create those views and then just show the dimensions by selecting them and doing different stuff. So you can go both ways per se. Okay, so this is a very important question with CAD. And basically what it comes down to is, can you make this? There's certainly lots of people who will go into CAD and, if you don't have the experience, you wouldn't know, but you're like, oh, I make this really cool thing, but there are restrictions in the real world if you can actually make it or not. Machines can only do so much. And I think it's a good understanding to have knowledge of that. So if you're ever going to be like, oh, I can make this thing, you might be able to make it, but typically there's optimizations you can make while in CAD to make sure that you can make it or not. So for instance, for this plate per se, most likely what you do is you start off with a big piece, a big sheet of metal. You take that, you put it on CNC, which would cut it out by just spinning this drill bit really fast and cutting out the thing around it. Then you cut out the inside, and then what it will do most likely is it will mark out the holes, which you'll go to a drill press and drill them out. And basically what that means is that what you want to have for any part you're ever going to make is you have that kind of that path in your mind of what steps you'll need to take to actually make it. Start with a sheet of metal, then using CNC, then use a drill press, then clean it up a little bit. And you'll have to do like little things like scrape it and all that stuff to like make sure that the edges aren't sharp. But there's a pathway already in my mind of like, oh, to make that part. So that's always a good question to ask whenever you're designing anything. Okay, so I'm going to go through a little bit of the uses of CAD. There's honestly a lot, especially, and you can see right here, the professional product design. Most modern mechanical or industrial engineers are using CAD in some way or form. It's integral part of modern engineering. But I mean, it is for a reason, because there's lots of things you can achieve when you have this kind of 3D space where you can do whatever you want. On the other side of CAD, there's also a lot of recreational use. People will just, work and they will go out and just design random things and just have fun and make things that just solve problems in their lives. Like personally, I've done that a lot. So for a little background, I did a lot of robotics in high school. I'm still doing a lot of robotics now. But I use CAD all the time in robotics. But I also, when I got home, I was like, well, I can, design. I also had the idea of like, oh, I could design something cool, to like fix a door hinge or, fix whatever, or, just make a phone holder. And I think a lot of the experience you can come with is just, messing around in CAD and just coming up with whatever ideas you can come up with. And I think that's how I learned a lot as well. And I'll go into more with the different programs you could use. So as I said earlier, there are many, many different programs of CAD you can use. As I say here a little bit, but I started off with Inventor. From like, I did Inventor for like 2.5 years maybe. And so, well, let me think about that. No, I did Inventor for like 3 years, and then I did like Fusion for like 1.5 years, I think, around that. But both are great programs. Both are free. So if you want to go out, right after this meeting and download these two, I would recommend it. Personally, now now at this point in time, I more recommend Fusion. It's great for beginners. So if you have no experience with any of this kind of stuff, Fusion's great. And there's like thousands of tutorials online. And same thing, next meeting will be, hey, we want you to download Fusion, and Fran is going to teach you basically what we are going to do there. And so I think it would be great, if you're interested, definitely download it before next meeting. But if you want to get it like even sooner than that, it'd be great to, just mess around and have some fun and learn something. There's so much to be learned. And I honestly do think it will help you in the future. There's other programs as well. Stuff like, basically stuff like Creo and Pro Engineer and AutoCAD. Those are all great ones. They're more industrial, as I said right there, so they use mostly in industry. So it's a little bit different, but they're also, I have experience with Creo because we actually took it as a class. It's actually ME 110 if any of you are ME majors. It's cool. I like it. I personally like Fusion better, but all of these are great programs. I believe Onshape is an online one, I think, right? And that is also another great one. All these, mostly the more recreational ones, are great starters. So I personally recommend Fusion, but yeah. Okay, any questions? I see there's something in chat, but I think I'm trying to access chat right now, so sorry if it's acting weird.
The thing in chat is just me talking about Inventor.
Oh, okay, nice.
I basically just said Inventor is Windows only, so just a
warning. Yes, I forgot about
that.
But
Fusion is not Windows only, and Fusion is the one that we're using.
Yes. So yeah, Fusion's great. It's very accessible, and yeah, it works with all programs.
So I just want to make it clear for me, because I'm kind of like a little confused. But so CAD is basically like a 3D modeling system.
Yep.
Okay. Okay. Thank you.
Yeah. It's I'm definitely going into much more detail with the next slides, but yeah, you come up with some idea, and then you're like, I want to, you know, because most everything we interact with in, you know, 2D space, or sorry, in 3D space is 3D, and, you know, someone had to design it. So someone went into most likely CAD and said, you know, I'll have some assembly of some object and I'll make it and, you know, be able to design it. And I'll go into a little more detail with that, but yes, yeah, that's basically it. Okay, so now I'm going to go on with the basics of CAD. I'll try to go a little faster because I maybe go a little slow. Okay, so to start with any CAD, you will need to know what a plane is. And a plane is the same thing. Hopefully you've learned this in, you know, whatever math class you're in. The plane is just infinitely wide and tall 2D space. And it's very important part of CAD because you will, as it says, you know, you will define everything based off the XYZ axis. So let's say if you're to make a cube, you make a cube, you'll say, this is, you know, 5 inches long, or 5 inches wide, and like 5 inches tall. And that is how you'll start to define whatever you want to make. If you're just making a cube, things will get more complex. But it's just the basics. That's the basics again. Another point. So you can create a plane at any time. That is true, and is very useful. Once you get into more advanced or intermediate topics, what you'll need to do is create new planes to like do different features. I'll go into more like why you would ever want to do that, but just know that you can make tangent planes, which is, you know, if you have some curve, make it tangent, then it will like be touching it just at one point, just what tangent means. And I'll show more examples later so it makes more sense. Okay, so CAD is based in sketches. So what I was kind of talking about, and this is related, the drawings thing where you're taking a 3D object and making it 2D, or starting with 2D and then going to 3D, you will need sketches. And sketches are great because you can either, like on the bottom, you'll see like the car. This is just like, you can make like a sketch of, you know, something that, this is what it will look like in 3D. But you can also, a sketch will typically start off where you'll select a plane, usually like the XYZ plane, and you'll draw some shape. And so that could be, you know, it could be a triangle, a square, it could be like some complex shape. But that's how you start basically every, most every 3D object. So I have this slide. I still love these emojis. Basically, what I'm going to talk about next is something called constraints. Because when you start working with this, these sketches, what you'll have is typically you have a lot of lines. Let's say you have some you know, weird complex object, or sorry, some weird complex sketch. You'll need to know about constraints to help you better draw these sketches and better constrain these sketches. So for this example, let's say for, you know, on the left, you see the circle is right in the middle. The only reason the circle is in the middle is because I went and I said, oh, the thing is 80 millimeters wide. I want the circle to be 40 millimeters, which is just half. So I want it to be in the middle. But what you'll see is that if I go back one day and be like, well, you know, my block is a little too wide, I want to make it a little bit smaller, and I make it 70, then the size of that hole, or sorry, the position of the hole will still be 40 to the right. So it will be off center. So it's like one of those things where I can go back in and yes, I can change it to 35 if I want to, but it's not really, it's not efficient, because what if I go back and I say I want it to be 90, then I have to go back every single time and make more and more changes. So there's a thing which is really useful, is something called constraints. Constraints are basically, they're geometric constraints. So basically you can, creating the relationship between different dimensions. Those are like 8 popular ones: the perpendicular, coincident, parallel, fixed, horizontal, vertical, tangential, and equal. And yes, as the third line says, it's a good point. These constraints allow you to create complex geometries that adapt to changes. So as what I was saying, that, you know, if I want the hole to stay in the middle all the time, I can do that doing constraints, and that's what's great about it. So if I go back in and I say, actually, you know, that cube or that, you know, rectangle or box I was making was actually too wide, I can make it even, you know, smaller, or I can make it even wider. And what's going on is that I set constraints. So for this example specifically, I had that rectangle I was looking at. I put the circle there. I put a line on each side of the circle. And then I put a line on the top and bottom circle. I did the I put the line on the edges of the box. And then what I did is, as you see in the bottom, I set lines 1 and 2 equal to each other and lines 3 and 4 equal to each other. Basically what that means is that no matter what happens, no matter how wide or tall or anything I make the box, I'll never have to go back and change where I want that hole to be, because it will always update to how wide the box is. And that's what's great. The CAD will do the calculations for you, and you don't have to go back and change everything every time. Additionally, as I said, the perpendicular constraint, I use that, so they will be that nice 90-degree angle. But like small things like this will save you, in the long run, will save you hours of time. Like I've gone through before, like not using constraints, and it's very helpful. So those are great things to learn. Okay, so you have some sketch, you like what it looks like, you think it looks good. In this example right here, you'll see it's, we started off with a square. So I just made a square, I defined some height, some length. And now I say, I want to make this 3D. So what you'll do typically in Fusion and other CAD programs, you will typically press E. That's not the case in Creo, sadly, but most programs, you'll press E, and that was E for extrude. Extruding, as said here, it gives depth to your sketch. So you start off with this square, and now you're going to a cube. And all you're doing is giving it, you're bringing it to the land of 3D, as it's stated here. But what that basically means is that you are leaving the 2D, and you are just setting a depth. So what I was saying about the cube earlier, that you could have 5 by 5, and then you're just saying another 5. So usually what it'll do is it'll ask you how much you want to extrude, and if you made that 5 by 5 cube, you'd extrude by 5 inches, and then you'll have that 3D representation. Okay, so before I go any further, this is an important distinction to make, because in the rest of like CAD and 3D printing and just design in general, this is important. So bodies, and this I'll be using this word a lot for the rest of the workshop, I think. Bodies, like 3D bodies, are just like that cube. You started with some sketch, you gave it a 3D depth, and now there's like, you can consider it that like there's stuff inside. It's not just like this hollow thing, it's like a solid cube. And so when you refer to like a 3D body, you're talking about something that by definition is solid. But there's also this thing called a surface. Surfaces are useful in many different, different like topics and focuses, especially for 3D printing. But all you need to know about surface is that a surface is that same cube, but there's nothing on the inside. You're just looking at the outside. There's just like air inside. And what it says here, and I think that's a good point to know, the surface of a cube versus body cube look the exact same. You wouldn't be able to tell the difference. But same thing, there are major differences. Like for one, that surfaces are much smaller part files typically. And so what that allows you to do is you can send more of the same, surface files versus the body file. A lot of 3D printing is done using surfaces. I'm going to talk about this more a little bit later about like what types of files, but just know that like when you're typically CADing, you're going to be making 3D bodies, but when you're using like 3D printing, those are surfaces, and they're typically called, they're called STLs. That's the file type. I'm going to go more into detail with this, but yeah. Oh, the other thing is that faces are very important. So that cube that we made, the 3D body that we made, that has 6 faces. And what the important is that, as I said, a face is just the side of a part. But what a face allows you to do is, if you go in the CAD software and you say, oh, I want to, cut a hole through something, like cut the hole through one of the faces, what you'll do is you'll do create sketch, and then you'll select that face, and you'll be able to make a new sketch and then follow that same pathway where you go sketch to extrusion. And so that's what you'll mostly be doing for all CAD is you'll be selecting faces, making a sketch, extruding. You know, that's a lot of what CAD is. So yeah. Okay, yeah. Any questions at the moment?
Or could you explain the body part of the cube? Like, so could you just explain the body of the cube?
Oh yeah, yeah. So the body of the cube, you can interject if you have any more questions, but it's when you took that 2D square and then you said I wanted to give it depth. So you give it depth and then it's the cube. And so the body, as I was saying, is solid. That's the biggest takeaway. The body is solid. So if you were to cut into this cube, there's like technically stuff in there because it's a body. But what I was saying is that surface, on the other hand, there's nothing on the inside. It's just, it looks just like a cube, but there's nothing inside. So like if you were to do that same thing where you extrude, you would never get a surface. You have to specifically like make a surface. But yeah, just know that the body is solid. Do you have any other questions?
Good, thank you.
Yeah.
Oh, I have a question.
Yes, Bennett.
So we brought up the idea of planes and faces.
Yes.
Do we kind of use them similarly in that we can sketch on them, but one we created as a physical object, one we created as a, I don't know, thought experiment? Like, could you elaborate on that maybe?
Yes, definitely. Good question. The difference is that a body or a surface will have different faces no matter what you will have a certain number of faces no matter what you do. So, you know, the cube has 6 faces, that pyramid would have 5 faces. And so if I want to make a sketch, I can just go to one of those faces, select whatever face I want and do create sketch. And I can go there and I can look at it and I can draw something and it will extrude. However, if I want to do something where, I want to cut something inside of, like, let's say, how about this? Let's say if I want to cut out a sphere inside of the cube, or sorry, I want to cut out a cylinder inside of the cube. Well, if I go to any of those faces and I say, okay, extrude and cut through, there'll be a hole on whatever face I choose to do the extrusion. Instead, what I can do is I can do something called, it's one of the planes, it's called a mid-plane. And so what that'll do is I select 2 faces and it creates a plane in the middle of whatever those 2 faces I selected, or whatever 2 planes I selected. And so what that allows me to do is I can make a circle on there and extrude it, and then there will be a cylinder inside of a cylindrical hole inside of the cube. So the idea, I guess the biggest idea to take away is that you can make a plane anywhere you want. But yes, you can make a sketch on a face or a plane, but planes are a little bit more they can be used in many more situations per se. You can make your own faces in a way, a little bit, not exactly like that. More that you can make a sketch wherever you want and then make an extrusion wherever you want. Any more questions, Bennett?
All good, thank you.
Yeah. Hope that cleared it up. Okay, so next topic is 3D modeling. So, we got this, whatever shape we have, the 3D body, we have this cube. And so now we're like, okay, maybe I want to do something a little bit more, make it, make it look nicer, make it perform better, whatever. So one of the things, this is pretty important aspect of CAD, is called a chamfer. You'd probably be using chamfer a lot. It's a very useful tool. And basically what this does is it adds an angled edge to whatever you're using. So with the context of this, this hinge kind of looking, or whatever, this kind of 45-degree angle looking thing, what I did is I clicked on that edge, and then now there's a triangle like connecting them. What that's basically doing is you're putting a nicer edge on things, that 45-degree slope. And the different scenarios, it can do different things. You'll see at the bottom that, I probably could explain this a little better, but in this case, the picture you see, it's actually adding material to make that that edge look like that. But in the bottom, because the edge, the one that you're selecting, is like already kind of exposed to space, it's actually removing material. That's what that at the bottom, I don't know if you can see, but at the bottom of both these pictures, there's like this kind of dark rectangle. That is because there is these edged, I put a chamfer right there basically, but it's going the other way. It's not adding material, it's removing material. And oh, so the uses. The use case for this is a big part is 3D printing, which is something, you know, as I said earlier, I'm very passionate about 3D printing. But the biggest thing to know from this is that if you have something, and I'll cover a lot more of this in the 3D printing workshop, number 3, is that anytime you want to make something 3D printed, most likely you want to add a chamfer to the edge. It just overall increases print strength. So if you were to try to like snap something, it's much more likely, less likely to snap if you have a chamfer on where, like, let's say you had like a square, you know, a square, and then you have like a rod coming up in the middle. If you have a chamfer at the bottom of the rod connecting to the square, that rod will be much less likely to break off. And the other thing it does is that I typically put a chamfer at the bottom of all my parts that I'm going to print. So that bottom edge I was talking about, that removes material. And what that does is it allows the part to adhere to the bed better. I'll cover more of this, why that happens. It allows the part to adhere to the bed better, and it makes the edges smooth so you don't like cut yourself or anything like that. Not cut yourself, but just, you know, it wouldn't be like too sharp. Okay, so next thing is the fillet. Fillet is also a very important tool. It's the same thing with a chamfer. It's you're selecting an edge of a part. So if you took that cube and you selected one of the edge and you press fillet, what you're doing is rounding it. So you're just putting a nice, like, you know, arc round to whatever is there. But it also goes conversely with the bottom picture. What you'll see is that you can round things the other way. I'm not sure the best way to describe this, but basically, as you can see, it is adding material versus removing material. Usually, from, you know, most stuff you do, you will be putting an edge on things where it like removes material. You don't add as material as much, you know, just to go off experience. But you're just putting a nice round of things. So same thing. Yeah, this is great for aesthetics. It looks better for sure. It is great for what's the other thing? Oh, so when I say reducing warping, so I'll go into this more detail the third one, but basically the short answer is when you 3D print something, as I'm a printer, I'm just a regular 3D printer, you print it, and as it's printing, because you're extruding hot plastic, it starts to want to cool because, you know, the air around you is much colder than like what what it's printing, and so the printer will want to the piece you're making will want to cool. So to stop it from cooling and then like coming off of the bed, you typically want to put a rounded corner on all of your part, like make all of the corners, the bottom corners of your parts rounded so that it does that less. I'll go into more detail with that, but it's very useful with this. This is another great use of fillet right here. And basically what this all comes down to is that you see on the right versus the left. On the left, there's very sharp, you know, 90-degree angles. But on the right, you know, you have those nice rounded corners on the outside and the inside. What that comes down to is the fact that the part on the left would be really hard to make in real life. It's close to impossible because of how we make things. And in this instance, what you do to make this part is you would take a sheet of metal, you get the, you know, whatever design you want, and then you put it on a CNC. And what the CNC is going to do is use an end mill. An end mill is just, you know, you have like a drill bit. Instead of doing like a regular drill bit, this one's actually flat, and it's meant to spin much faster. And what you're doing is you're spinning this drill bit so fast that you're cutting through like metal sheet. And so what we do in this scenario is that you take that sheet, you put it on the bed, you get it all ready, and you start it to go using, using the shape of this part. You'll create something called G-code. I'll talk about that more later. But basically what that does is you tell the CNC head where to go and cut things. And so when you go to cut things, you'll see that, as I was saying, the end mill is just kind of like a drill bit for like a drill. And the whole thing is that it's circular. So when you go to cut something, when you go to cut like the interior of something, you can never end in a rectangle. You can't remove the material. It's impossible, So you have to make that rounded edge, because what will happen is it gets to the edge, there'll be material on the top and on that corner that it just can't reach because it's it's a circle. So what you have to do is make these rounded edges on the inside. On the outside, it is possible to get those nice like 90-degree edges, but it's still, it's just easier for the machine to cut at that nice curve. And same thing, most, any machine you're going to use, it can sometimes be better to, just make whatever you're doing, not try to make any like sharp movements, because, especially for a CNC, you'd be going, straight and then down, versus if you'd be going like to the right and then down. Or what you could do is you go right and then nice curve and down. So that's what fillets are great for. There's machining limitations that you should know about when you're designing things, so that you can make things that are realistic. And I would argue the thing on the left looks cooler than the piece on the right. Sorry, the thing on the right looks cooler than the one on the left. And the fact that, this is actually realistic. This is something you could make. Okay, that was a lot of stuff. Any questions? Okay, if that is the case, I will go on. I believe this will be my last section. And then Okay, so you have your part, you have whatever you wanted to make or made. Let's say, for instance, that cube I was talking about. And now you're saying, I want to put a hole into it. So what you can do is same thing. You can go through and select one of the faces, create a sketch, draw a circle, and then extrude that circle through the body of the cube, and then the interior of that you'll have the hole. Oh, that's one thing I didn't cover that I should have covered. When you extrude something, you can join or cut. So I probably should have mentioned this earlier, but for the instance with the circle thing, if I were to extrude that circle, I'd be selecting cut instead. So it means I'm removing material. Based on what I was talking about before, that cube is a solid object, but what I'm doing when I do the extrusion cut is I'm removing all that material in the middle. And so I could go through and do all this, and I could get some diameter, whatever, spacing, wherever I want it to be. And it works out good. However, there's a better option. There's something called the hole tool. Let's see what they'll do, and I know Fran will go through this in the next workshop, is that you select a point. You still have to make that extrusion, you still have to make that sketch. You'll make that sketch. You'll create a point, which is just another thing you can create in a sketch. You can create points and sketches, points and lines and arcs and other things. Select the point, you'll say where you want it to be, and then you typically will press H. And so what H will do is it'll do the hole tool. Not every program you press H. Not every program has a cool little quick keys to do these things. But the hole tool, what it'll do is you can select what type of hole you want. And so if you don't know anything about, you haven't done this kind of stuff before, and you're like, oh, what kind of, what are you talking about? Basically, there's all these different types of screws in the world, and they're all dictated by either typically the US system, which I believe is ANSI, so ANSI, or the metric system. And so they have all these numbers around them, and you don't know any of the numbers, that's fine. You just need to know what you need. So you could get like for the, I go like, what was I saying? Like for the US system, let's say you need a hole that can fit a 1/4 screw. And so what you'll do with the hole tool is you can select that, they has all the database on there of like every single screw you'd ever want. You'll select that hole, you'll put in, the values, you can like drop, select it. But what'll be nice is that you can say what type of hole you want. And one of the things you can add to the hole is the center bore and the countersinks. And so I'll go in my next slide will be all about that. But the other cool thing about this directory is that, as I was saying, you don't need to know anything about the screw. All you need to know is what it's called. And what that allows you to do is you don't need to look up like how big this hole needs to be. Because what you can see is, this is a whole other topic, but actually I'll give a good example right now. So just in general with any type of engineering, if you have a hole, let's say that is 2.0000 inches wide, and you have like a shaft or something that you want to put in there, the shaft can't be 2.00000 inches wide. It has to be like 1.99999 inches wide, because you need space for things to go into other things. That's like a big principle of any type of engineering or design that you do. So what you'll do, and why this tool is so useful, is that you'll say, there's different kind of, talking about that tolerance, so I just talked about it, it's called tolerance and clearance. What you'll do is you'll set, I want a 1/4 screw, but I want like, you'll say like, I want like a free fit. And a free fit is that you can very easily push something through. It's like super easy. Something also called an interference fit. And an interference fit is basically, it's very hard to push something through. It's like very tight. So when I say that, the reason is because in that very tight situation, the shaft is very close to the size of the hole. But in the free fit situation, the shaft it's smaller compared to the hole. And so that is why this is so useful, because you can just switch through those things very quickly. Instead of, looking up how big should a 1/4 clearance hole be, you can just pull up the little list and it will show you, this is how big it should be. So yeah. So the other cool thing about the hole tool and what makes it useful is you can add other things called, these things called counter bores and countersinks. So yeah, the goal of this thing specifically is you don't want your screws to stick out of the top. And so that the surface will be completely flat. So what that means is like, if you ever seen something that is designed, good or has like good engineering behind it, you'll see that like, none of the screws typically are sticking out. They're like recessed into the part. And so what that is that when they designed this, whoever designed the part, they left a little space inside of the piece for the head of the screw to go in. And so the head of the screw sits there. And so same thing, the entire surface is then flat. And so there's many, many different types of screws, but largely there's like a flat one on the left, and on the right there's like that angled one. And so both, it's different styles. So the counter bore is for the one that's like kind of flat, and then the counter sink is for the one that's angled. And so both achieve the same goal in the end. You have a flat surface on the top, but just different screws, different material. Okay, so this has nothing to do with, well, you can use it with holes, but it's something completely different. The pattern tool is very useful. Basically what it does is it allows you to copy one or more features and multiply it across one or more directions. And what that means is, let's say you make your hole. It has, nice countersink on it. It's ready for whatever screw you're going to put in there that, fits nice and flat into there. But you're like, oh, my part actually needs like 20 more of these screw holes. Well, what you could do is you could go through and, make a point for each one of those holes, or you could, even worse, you could go through and make a circle for each one of those spots. And you can go do that and it'll work just fine, up until when you need to move something or, do whatever. Or on the other hand, you can use the pattern tool. So the pattern tool, as you'll see in this bottom little animation, is that you take some, some object or some feature or some sketch. This works for most anything. So you could do this, you could pattern a body. So you could, this is more advanced stuff, but if you have that cube, you could say, I want to pattern this, and you can pattern it along the x-axis. So you can make like 6 cubes next to each other just for fun. Or you can do it with the same thing as I was saying, the hole tool. And so you say that I want 3 more of these holes in this pattern, this rectangular pattern. Typically, there'll be, for patterns, you can define it a rectangular pattern. You can do a circular pattern. So if you have some cylinder and you want to put a hole on one side of the cylinder, you can rotate it around the central axis of that cylinder, and you can make like 6 holes around it, all spaced by like a certain number of angles. But for the rectangular pattern, what you'll do, oh, sorry, wrong way again, is you'll define a distance, how far you want to space it between each piece or each like copy per se. Or what you'll do is you'll define, like I want it to, you can define something called span. And what that'll do instead will be like, I will start here, I will start here, and I want it to go here, and I want 6 holes to be in that space. And so you can define it that way as well. It has different use cases, but both are useful depending on your situation. Yeah. Okay, so mirror. This is another useful tool. And so same thing. It's like pattern. You spend all this time and energy and work to make this one side of a thing, and you're like, oh my god, I have to make that again. So you go through and you could design and do the exact same thing over again, and like, oh, I think I measured like this here and did this here, and like you can get it as close as possible and be like, you get it right, or maybe you mess up a one dimension and something is off by just a little degree. Or you can use the mirror tool and just copy all the work you've already done and just make it again. And it's a great time-saving measure. Same thing with the pattern tool. But it's also nice because back to why you should put constraints on things, why you should do pattern tool, is because everything else you make is based off of what you started with. And so it's updating as well. So what that means is that, same thing I was talking about earlier, is that you make a change to something and the copy will reflect that because everything updates. So same thing with the constraints. If you make a cube wider or thinner, your things will update. And I'm telling you, it saves so much time in the end because you don't have to go back through and update these things manually. And I think that's a big thing with like, you could go from going from basics to intermediates, and like something to definitely learn if you really do want to get into CAD is like using these tools. You can do a lot of things. I mean, there's so many other features in CAD that you can use, but like knowing these tools and like a few others allows you to save so much time and like just make your workflow so efficient. So yeah. Another cool tool is something called the loft. This might be something where you're like, oh, when would I ever use this? I've actually, surprisingly, I've been using it a lot recently. It's pretty useful. Basically, you do, sorry, one sec. I forgot to mention something. When you do the mirror, what you typically do is you reflect using, you reflect over a plane or a face. So in this case, I created a plane on this edge right here. You see the orange rectangle thing? I created a plane on this face, and then I reflected over this plane. However, what I could also do is say, oh, I want to reflect where the big circle is. I want to reflect right off that. You can do whatever you want. You can also, if you want to put space between the two pieces when you reflect them, there's something called an offset plane. It's basically, you select some face and you say, I want to go 3 inches away from it, and then you'll create a plane there, which is, parallel to that other face. So you create space between those 2 points. Okay, now back to loft. So what a loft allows you to do is you'll create a sketch at one place, and then you'll create a sketch in another place, and then you'll say, okay, I want the CAD software to connect those 2 sketches. And what you'll do with that is you'll create a 3D body. And this is a great use of the offset plane. That's how I made this part that you'll see right here, is I started with a circle, and then I clicked offset plane, and I offset it. I offset a plane that was parallel a certain distance away. And that's how I got to, and that offset plane, I created that square. That's how I made that. And so as you see here, the CAD program by definition connects them in the most efficient way, but you can basically you can connect things however you want, per se. That might sound a little weird, but as you'll see in the bottom right, you see how you can change some settings and change how things look. And like, see how it's like angled now and they're both angled in? And so the reason I bring that up is, if you ever want to design, let's just say like a vase, one of the better ways you can create a vase in CAD is you could, let's say you have a couple different circles on all different offset planes. You can connect them all using the loft tool, and then you can edit how they bend in and curve and do whatever. So yeah, that's one of the bigger uses. I've used it for a lot of different things, especially for design and some of like my more personal projects. But it's a great tool. So next thing, this is another useful, more intermediate tool, is something called the shell tool. The shell tool is something, I think I'll just go through what it says. I think this best describes it. But you create a cavity in your 3D body that is open on the face you select, but has internal wall thickness on other faces. So basically what that means is you're taking that, this weird shape I made with the loft last slide, and now instead it's a cup. So, you can make a lot of these things, that is the basis of, what a cup is. You add like a little, little handle on the side, but other than that, it's a great use case per se, if you ever want to make something like that, a cup or a vase or anything like that. But there's other, more important use cases of like with engineering is that you save material and weight. So what you can do is, most of the time, and you'll see this, is that, most of the time, even for 3D printing, is that the thing that is failing is not because the entire thing isn't like completely full of plastic. There's a concept in 3D printing workshop, which I'll cover in the third one, is that something called infill. So you can choose how much of a 3D printed part you want to be full of plastic versus just empty space. And so at a certain point, you realize that like adding more plastic to the inside doesn't make the part necessarily stronger. It makes it by a little degree, but more how you design things is a big indication of how strong your part's going to be. And so what's great about the shell tool, and what you'll see if you get the chance to use this, is that you can save a lot on material without decreasing your strength, or decreasing your strength by a insignificant amount. So it has a lot of functional use cases. Another, just a little note, but this is a useful aspect of CAD, is that you'll see in the bottom right that, maybe like, oh, what are we looking at? But what this is we're actually looking inside of the cup. So what I did is I did something called a section view. So I selected one of the faces and I said, I want to see what's inside of that. So what we can do is basically, you select the face and then you cut to whatever, like you cut to the left. In this case, you cut to the left. So now you can see inside of the cup. And so what you'll see is that the red area with the lines that go is, it's like the inside of the cup. And so the reason why is like section views are important because you can see inside of your own parts, you know, in different angles you wouldn't be able to see before. I'll show a little bit more here, but this is some shell tool customization. So you see that, you know, I took this same shape. I haven't done anything to it. I'm using the exact same shape. And you can do different customizations for shell. What you'll do is you'll select the face, and you'll also select the thickness of the material that remains, or like what would be called the wall thickness. So in the first case, the standard, you'll see that, you know, the red area isn't that thick because the walls aren't that thick. But in that same scenario with the same face selected, but you have higher thickness, see how there's more red now? That's because if you were to look on the inside of that cup, the walls are much thicker now. And so, and then also with the different face, you'll see that things change. So now instead of the top being, you know, gone, the circular part is gone and the top is there because I selected the circle now, not the square. But yeah, I guess this was a lesson, but mostly in the, you know, the section viewers are very useful. It allows you to see things you'd never see before. And the shell tools are useful. Oh, the one other thing I'll say, because I don't think I commented on this, but the shell tool is usually accessed. You'll go to like view or something like that. You'll select a face you want to look at, and then you'll select a distance from that face inside of the part. And then what the program will do is it will visually cut whatever. So you'll have some distance between the face and that plane, and whatever's in between there, the software will visually get rid of, so you can see the inside of a part, and then you'll see like the other side of your part. Yeah. Okay, any questions? Okay, if that is the case, then I believe this is the last slide. Robot does a little jump. But yeah, I think this is basically it. There are many, I'll have a little ending note, but there are many other things that, you know, you'll find in CAD, and there's many other topics. You know, I only covered a fraction what could be done, but I think you'll see that, you know, just by learning some of these more basic stuff, you'll be able to access, you know, higher learning per se. So if you go into CAD and just start messing around, you know, just try out using the shell tool, try out using the pattern tool. You'll realize over time that, you know, these things will make, will optimize your time, and then you also have a better understanding how the world works around you. I'll say a note on just the general workshops. I didn't put this in the slides per se, but this will be probably the formatting for, well, it's going to be a little different for the other workshops. Basically, same thing as it was asked earlier. We're going to be doing, you know, 6 of these. You've done 1 already, which is great. But there's going to be like 5 more of these, but it'll be the same thing. It'll be an hour, you know, long. Hey, this is all these cool things, and, you know, here's more to learn about them and other things. Next week will be a little bit more hands-on. So sorry if this was maybe, you know, not as interactive as points, but next week will be, you know, take these things that I talked about and learn, and you'll actually go into CAD and you'll design that arm that I was talking about on the robotic arm. Because we need to, you know, design these things using all these principles that I talked about. And yeah, and then after we'll move into more of the code aspect sort of things for workshop. Well, sorry. We'll go CAD with Fran, then it'll come back to me where I will talk about 3D printing. I'll go through everything you ever want to know about that, the use cases, you know, how to optimize your design to make it print better. And then we will go into, you know, this 3-stage computer science aspect of things after that point. So I'll say, Bennett and Fran, do you have anything more to add?
Not really. I know that, yeah, so basically we're going to send out instructions on how to get Fusion before the next workshop, but included in the next workshop are instructions on how to get Fusion if you don't manage to do that before time. And things I recommend to bring to it, I guess, you should probably bring a mouse. It's always good to have. And you can also download it onto your laptop, but if your laptop is not like If you like have a bad laptop basically, then I would recommend using like a PC if you have access to one. That's it. That's all I have to say.
Nice. Thank you, Fran. Brendan, anything with you?
No, I'll just say that there'll be a lot of setup for the workshops for like the first programming one, which we'll make sure to send out probably 2 weeks in advance. So we'll let you know about it next week just to make sure you have some time, because there are a few steps that we've written out, of course, but they do take time.
Yes. Thank you, Brendan. The biggest thing is, if you want more information, the CCC website is a great resource, and that event registration site is a great resource. We'll definitely continue to keep sending out emails. What we plan to do, I mentioned this earlier, but we'll be having office hours for all of our workshops. So basically what that means is whoever taught the lesson will be available for like an hour outside of this to just answer questions if you have any. I believe I'm gonna host mine like next Wednesday at like, I don't know, from like 8 to 9 is the current plan, but that's on the CCC website. We'll keep updating that. When I say CCC website, there is, I believe, I think I have it pulled up. Sorry, just one sec. Okay. Basically what that is it details all of the information you could find on us and the workshops. Hopefully you guys have looked at it before. I don't know. Don't want to assume, but it basically includes any information more you could learn about what we're doing. Where is it? Okay, I think I found it now. Sorry. Okay, let me share my screen. New share. Okay, should be able to see that now. Yeah, so hopefully you've seen this before, but this will be, a big resource if, hopefully, I hope you all continue doing this. But we have more information like, hey, this is where office hours will be. These are the videos. Oh yeah, so if you have any friends who, didn't make this, but they're still interested in maybe what I said, hopefully, then we're gonna be posting the videos for this like tomorrow, hopefully. And then after every workshop, we'll be posting a video, basically for one, document what we've done, and for two is that you can go back and watch this if you need any more help. And same thing, I know all of us here, if you have any questions about anything, just drop us a message or, drop us an email. We'll be glad to help if you have any questions. And yeah, so I guess in closing, thank you all for coming. I very appreciate it. We definitely appreciate you guys here. I hope you got something out of this. I hope that it was, interesting and useful. And, I think this was made, especially I know for this team, I think we made it with a lot of passion in our hearts. Like we definitely want to make this as accessible as possible, and we want to teach as many people as possible. So if you have any comments or concerns, just tell us. And yeah, so thank you for coming. I can't think of anything more to say, but yeah. Bennett, do you have anything more before you go?
Yeah, I put the link for the workshop site as well in there. It just details all these things we've kind of just covered. I guess Joe has it on screen obviously right now as well. But Joe, in the middle of your screen right now, it says GitHub is here. Would you mind clicking that link, please?
Oh yes. So oh yeah,
Brandon, you go ahead. I can summarize it, but yeah, if you look Benedict on the top left there, this is on my GitHub account, and we'll cover exactly what that means. But this is basically a thing that's used widely in computer science to share code or to collaborate on code. And so later in the workshops, we'll be downloading this onto your machine if you want, and you'll be able to run a lot of the demos and edit the exercises on your machine, in the setup. So that's where it is. If you want to look at what it's going to do, Joe, if you scroll down on this main page here for the GitHub, it details which workshops which, and if you go into workshop 4, the instructions to set everything up are there. But all the content is already online between the GitHub and the slides linked in the website. So definitely, wait for the videos if you'd like, and wait to do things live. But if you're interested in, seeing what we're going to be doing, it is all right there. It looks like a lot, but we do go through a lot of useful things as well. So Just heads up on that, I think.
Yeah, and it's not. It may look scary at first, especially as I was saying, I'm not a computer science major, but I made it through and I learned a lot of stuff, and it's definitely accessible if you have no experience with any of this kind of stuff. That's been a main goal of what we've been working on. So yeah, okay, awesome. I think I'm going to end the recording here. Yeah, thank you all for coming. We all very much appreciate it, and yeah, I hope you learned something. Let me.
I have a question real quick.
Yeah. What's up?
So by next week, Friday, we would